Okay, this is SOA Sample C exam problem number 288 from the fall 2009 exam. For a survival study, you are given 1. Deaths occurred at times y1, y2, and so on until y9. Number 2, the Nelson-Allen estimate of the cumulative hazard function at y3 and y4 are 0.4128 and 0.5691, respectively. And number 3, the estimated variances of the estimates above are, the variance at y3 is 0.009565 and the variance at y4 is 0.014448. And the problem is to determine the number of deaths at y4. This is the solution to number 288 from the fall 2009 Sample C exam. We have that S4 over R4 is equal to the estimate of the hazard rate at y4 minus the estimate of the hazard rate at y3, which is given as 0.5691 minus 0.4128, and that equals 0.1563. This comes from the review sheet that we're going to hand out in class. It's the hazard rate at y4 is equal to the hazard rate at y3 plus S4 over R4. So then that's how you get this. So then we're looking for the estimated variance, and that is going to be the summation of from I equals 1 to j of SI over RI squared. So then we have S4 over R4 squared, and it's going to be the estimated variance of the hazard rate of y4 minus the estimated variance of the estimated hazard rate at y3, and that gives us 0.004883. And then to find the number of deaths at y4, or S4, where it's going to be S4 over R4 squared divided by S4 over R4 squared. And that's going to give us 5, and in the multiple choice, that's answer number D.
Okay, now this is the sample C problem 252. We have a sample of 10 payments just with these numbers, and the plus sign means that's censored data, meaning that this number here could be 11, 12. It's something greater than 10, but they cut off at 10. And now our goal is to determine Greenwood's approximation to the variance of the estimate of S hat of 11. The first step to solving this type of problem is that we need to develop a table like I have here. And our goal is to solve for estimated survival function of x, and then we're going to later use that function in our Greenwood's approximation. So what does all this mean? Well, first thing I did was I wrote down all our yi will be all of our uncensored data. We need the uncensored data like that, and the 5s, the 10s. Since it's only censored data, we won't write that down for now. And our SI is basically just counting how many of our yi's we have in our data. So for 4, we just count how many 4s there are. 1, 2 4s. 8, there's just one of those, 12, and so on. And then for our RI, which is our risk set, we count how many of the data is greater than or equal to 4, or 8, or yi, basically. So in this example, for y equals 4, we count all of them, including the censored data. So that would be 1, 2, 3, 4, basically all of them. So that would be 10. Then when we get to 8, we'll count all of the ones greater than or equal to 8, which is just 1, 2, 3, 4, 5. And even though that we have some censored data here, these numbers could be greater than 8 or less than 8, we don't know. But since we don't know, we're just not going to include them. That's how the rule works. And so we did the same thing for 12 and 15, and not as interesting. So then that gets us to our formula for Kaplan-Meier. And anytime we use Greenwood to do it, when it says product limit estimator, we need the Kaplan-Meier estimation. So our S hat for at 11, we use our formula going up to all numbers less than or equal to 11. So our RI is 10 minus 2 divided by 10, which is right here. And then we go for 8, 5 minus 1, divided by 5. So we simplify that, and we get 0.64. And at this point, we did the hard part. We just have to follow the formula for Greenwood's approximation. So the first thing we did, we got the S hat of 11. It's right here. We're going to square it. So 0.64 squared multiplied by sum of all this junk. So we have SI is still equal to, divided by our RI, which is 10. 10 multiplied by 10 minus 2. And again, for y, I equals 2. So the yi equals 8. So that would be 5 times 5 minus 1. 1 divided by that. Sum it up, multiply it together, and we get 0.03072, which is our answer.
Okay, so now we'll be doing SOA sample problem number 16. And we're given this data set of the time, number at risk at this time, and the number of failures or deaths at this time. And we want to know the probability of 3Q1, which is defined as the probability of failing at or before time 4, given survival past time 1. And we want to use Greenwood's approximation to find the variance of 3Q1. Okay, so taking this data set, we're trying to find 3Q1, which is defined as surviving 3 additional years after you've already survived 1 year. So this written, in other words, is the number that survived to year 1 minus the number that survived to year 4 all over the survival, or the number that survived to year 1, which is consistent with conditional probability. And simplifying that with algebra, that's equal to 1 minus S of 4 over S of 1. So this essentially is saying you take the survival, or the variance when you're approximating with Greenwood's, is you're approximating the variance for S of 4, but only using the data set of people that have survived to year 1. So like, to keep looking at this data set, you can basically cross out this first row right here, and you only need this chunk of people. And you want it to 4, so you can stop here, and you only focus on this chunk of our data. So if we look over here at the formulas for Kaplan-Meier and Greenwood's, we see that for Kaplan-Meier, S of j is equal to the products of all your risk set minus the number of failures in that time divided by your entire risk set. And you take the product of that all the way until you get to the number at t that you want. So here you're trying to estimate S of the survival function to 4. So you take the second time, because you're ignoring the first time, and you have your R sub j is equal to 27. And then your numerator is R sub j minus S sub j, which is 27 minus 9, which is 18. And you do the same for 3, so you have 32 minus 6, 26, minus 32, or over 32. And then you have 25 minus 5, which is 20 over 25. And you stop here because you want S of 4, not S of 5. And you multiply all this together and you get 13 over 30, which is your approximation for S of 4 using Kaplan-Meier. So then you look at your Greenwood's approximation for variance, and the equation is your approximation for the survival function to t squared using Kaplan-Meier, plus the summation of your S of I over your risk set times your risk set minus the number of people that expired at this time. And one thing to note is that for this one, you basically have to use the Kaplan-Meier first before you can move on to this part. So it's like a 2-step process. Okay, cool. So here, the first part you already did. So the approximation of S of 4 using Kaplan-Meier is 13 over 30 squared. And then here you take this equation, this part of it, and you have S of I at time 2 is equal to the number of failures, which is 9, over the number of your risk set, which is 27, and then times the number of your risk set minus the number of your failures, which is 18. And doing the same for this, you have 6 for failures, 32 for your risk set, and then 32 minus 6 for this section of that equation. And vice versa for 4, you have 5, 25, and 20. And taking this entire thing and putting it in your calculator, you get 0.0067, which is answer choice A.
Okay, this is SOA problem from 17, using the same data set that we used in 16. And for this problem, we're going to calculate the 95% log transform confidence interval for H3 based on the Nelson-Allen estimate. find the log transform confidence interval, first we need to find the h hat of 3. And to do this, we take the failure at time 1 divided by the number of risks, plus the failure at time 2 divided by the number of risks, plus the failure at time 3 divided by the number of risks. And that comes out to be 0.6875. And then next we find the h hat of 3, the variance of that. And that is simply the number of failures at time t divided by the number of risks squared and we do this sum it for time 1, 2, and 3, and that comes out to be 0.02376. Okay, to find the confidence interval, we're going to do h hat of 3 times u. And u equals the exponential plus or minus 1.96 because it's a 95% confidence interval, times the square root of the variance hat of the h hat of 3, all divided by h hat of 3. And remember, we found these numbers earlier. And then doing this, u simplifies to exponential plus or minus 4.3495. And we get the interval to be 0.443, 1.067, and this is answer choice D.